In this second lecture on numerical integration, today we shall discuss Simpson one-third rule. In the earlier class, we have discussed about Simpson about trapezoidal rule. In trapezoidal rule, the actual curve between two consecutive x values have been replaced by a straight line fit or a linear fit, and the resulting quadrilateral is a trapezoid, and hence the name trapezoidal rule was given. As we approximate the curve by a straight line, it is obvious the result may not be good enough, or we may require a large number of points in values to get desired level of accuracy. To improve this approximation, we then go to Simpson one-third rule, in which case the integrating polynomial is a quadratic one. Simpson's one-third rule, where the integrating polynomial is a quadratic one, that is, the curve, the shape of the curve is parabola. So we assume phi m of x as phi 2 of x, which is a0 plus a1x plus a2x squared. This is the basic assumption, and as before we use the definition that the integration a to b f of x dx is the area under the curve. So we consider a0 and a0 as x and an as b. As before, we use x0 is equal to a, xn is equal to b, h is equal to b minus a by n, etc., and x I is equal to a plus ih, the same that we used in trapezoidal rule. Firstly, we want to we divide it into certain intervals. We first want to get the result starting from x0. So we want to calculate this value fx dx from the limit x0. I am not keep writing the upper limit right now. I will. This exact value is being approximated by phi 2 of x dx, x0, upper limit is. Now we write it as a0 plus a1x plus a2x square dx integrated from x0 to some values. Now you see that in the case of trapezoidal rule, the corresponding part was a0 into a1x dx, and there were two unknown constants which can be evaluated from two conditions, x0 and x1. That is, we know y1 is equal to a0 plus a1x x1, and y0 is equal to a0 plus a1 x0. There were two conditions, and two conditions were sufficient to find out a0 and a1. But here there are three unknown constants. So to determine three unknown constants, we require three conditions. So the condition would be the values of x0 y0, x1 y1, and x2 y2. That's why the limit should not be x1, rather it is x2. I think the point is clear. So then for the next block, this is the first block or A0 block. Then for next block, the integration will extend from x2 to x4. That is to say, the entire interval has been divided into an even number of intervals. There were no such restriction imposed on trapezoidal rule, but for Simpson 1/3 rule, it must be even. N must be even, and you see the limits are not x1 but they are x2. If we go to a polynomial of degree 3 as we used to do in Simpson 3/8 rule, in Simpson 3/8 rule, Simpson's 3/8 rule, phi m is equal to phi 3 is equal to a0 plus a1x plus a2x square plus a3x cube. There were 4 unknown involved, so the first block formula in this case would be phi 3 dx between limits x0 to x3. These 4 condition enables us to determine 4 unknowns, and in Simpson 1/3 3/8 rule, n must be 3m or 3l. L is an integer, so the number of division in which one should divide the entire interval in Simpson 1/3 rule must be an integral multiple of 3. This is an extra condition that has to be taken care of. In trapezoidal rule, the interval may be anything, but in Simpson rule 1/3 rule, the interval must be an even one. In Simpson 3/8 rule, it should be a multiple of 3, and if we approximate the exact function by a 4th order polynomial, then the interval must be an integral of 4, and so on and so forth. So if we integrate this, we get a0x plus half a1x square plus 1/3 a2 x cube between limits x0 to x2. So that is to say a0 x2 minus x0 plus half a1 x2 square minus x0 square plus 1/3 a2 x2 cube minus x0 cube. We take x minus x0, x2 minus x0 common all alone. So we are left with a0 from this term. This is half a1 x2 plus x0, and from this part 1/3 a2 x2 square plus x2 x0 plus x0 square. We have written a cube minus b cube is equal to a minus b, which is taken common here, and a square plus ab plus b square formula. Now you see that x2 is equal to x0 plus 2h as for this formula. So this is 2h, and for this part we have a0 plus, this is x twice x0 plus twice h, half is adjusted, so this is a1 x0 plus h. And coming to this part, If we write this, it is x0 square plus 4x0h plus 4h square, because actually it is square of this, plus x0 square plus twice x0h from this term, and this is x0 square. So altogether this is 2h, a0, a1 x0 plus h, and we have 3x0, so this is x0 square, 2 6, so 2 x0h, 4h square, 3 is taken common, so 4 by 3h square as the result. So we rewrite this final result. Twice h, a0 plus a1 x0 plus h plus, sorry, this is 2, a2 x0 square plus twice x0h plus 4 by 3h square. Now our aim is to find out or replace the expression within the square bracket in terms of a combination of y0, y1 and y2. The analytical or rational way would be to write the expression for y0. y0 is a0 plus x1, a1 x0 plus a1 x0 square x1 which is equal to a0 plus a1 x0 plus h plus a2 x0 plus h whole square, and y2 is equal to a0 a1 x2 plus a2 x2 square, which is equal to a0 plus a1 x0 plus 2h plus a2 x0 plus 2h whole square. The analytical or rational way would be to solve these three equations for a0, a1 and a2, and to replace these a0, a1, a2 over here in terms of y. But the thing is a complicated one, as we have to solve these three simultaneous equations. Rather, guided by the experience, we consider this quantity y0 plus 4y1 plus y2. So for y0 we write a0 plus a1 x0 plus a2 x0 square plus 4 a0 plus a1 x0 plus h, rather write first step as a0 plus a0 plus a1 x1 plus a2 x1 square plus a0 plus a1 x2 plus a2 x2 square. Now the result is first 6a0, we have 6a0 plus a1 taken common, it is x0 plus 4x1 plus x2 plus a2 taken common, This is x0 square 4x1 square plus x2 square. This is equal to 6a0 plus, you see that this is, let me write it first, 6x0. There is x0, there is 1x0, there are 4x0, so 6x0. There are 4h plus 2h, 6h. Now coming to this part. This part is basically x0 square plus 4 times x0 plus h whole square plus x0 plus 2h whole square. So the x0, so for x0 part is concerned, this is 2x0, 4x0, so 6x0 square. Then x0h, there are 8x0h and plus 4x0h, so this is 12x0h, and h square, there are 4h square and there is again 4h square, so 8h square. This is the if we take 6 common all along, we get 6 times a0 plus a1 x0 plus h plus a2 x0 square plus twice x0h plus 4 by 3 h square. You see the quantity within the square third bracket over here exactly matches with this. So to say, we can write it as this thing divided by 6. So we write it as 2h by 6 times y0 plus 4y1 plus y2. This on simplification becomes h by 3 y0 4y1 plus y2. This factor 1 by 3 is the origin for the name of 1/3 rule. This is the block formula for Simpson 1/3 rule. This is the block formula for Simpson 1. Now coming to the composite formula. Composite formula, we write f of x dx from x0 to xn. We approximate it by phi 2 of x dx from x0 to xn. That is, we write it as integration x0 to x2 phi 2 dx plus x2 to x4 phi 2 dx, then x4 to x6 phi 2 dx, then finally xn minus 2 to xn phi 2 dx. And for each step we write h by 3 is common. H by 3 is common. For this we have y0 plus 4y1 plus y2. This is from this contribution. For the next contribution, it will start with y2 plus 4y3 plus y4. This is the second contribution. Then y4 plus 4y5 plus y6 and so on and so forth. Lastly, we have this is yn minus 2 plus 4yn minus 1 plus yn. The last but one term is, let me write the last one but one term that would be helpful for you. The last term is, you know that yn minus 2 4yn minus 1 plus yn. This is the last term. The previous one would be yn minus 4 plus 4yn minus 3 plus yn minus 2. So if we collect the term, we see the first and last term appears once. So we have h by 3 y0 plus yn. Now the odd terms appears with weightage 4. So 4 times y1, y3 right up to yn minus 1 plus this term having the weightage twice. So 2 times even number of terms excepting the terminal ones. So to say, we write it in compact form. I is equal to 0 . So this is the composite formula for Simpson 1/3 rule. So this is f at x is equal to a, this is f at x is equal to b, and these are the intermediate values. We have divided the interval into an even number of equispaced intervals, and within a block which comprises of 2 strips, that is, a block has, in Simpson 1/3 rule, a block has a width of 2h and it is being replaced by a suitable parabola. One thing I like to make it clear, the shape of the parabola changes, or the parabola under consideration changes from one block to another. As for example, the parabola in this block is in general not same to the parabola of the other block. This parabola is different from this parabola. As in the case of trapezoidal rule, the straight lines were different in for different segments. Similarly, the parabolae that we use in Simpson 1/3 rule changes from one block to another block. Another point that I want to make clear, that it is a common concept to the people that numerical integration means we ought to divide the interval into a large number of intervals. As I have seen in yesteryears that the students generally at first sight sets the value of n to 10,000, and they argue that the numerical integration will give you convergent result only for high values of n. No, it's a misconception. The number of points that would be required depends on the nature of the integrand under consideration. The number of points that would be required to get a convergent value of the integration depends on two things. One, obviously on the nature of the integrand, and secondly the method that we are using, that is the nature of the integrating polynomial. If the nature of the integrating polynomial fits with the actual function, then we can get convergent result with very few points. As for example, if the integrand under consideration be a straight line, then we can get convergent result using trapezoidal rule by only two terminal points only, because let the integrand is of this sort, and we are to integrate from a to b. If we use trapezoidal rule and we use n is equal to 1, then a single straight line is used to fit this, and we will get exact result with n is equal to 1. There may be slight deviation from the analytical result, that is due to the truncation error in numerical analysis, nothing else. On the other hand, if we have the integrand in the form of a parabola, integrand is of the form of a parabola, and we want to integrate it by trapezoidal rule, then we are to replace the parabola by segments of straight lines. So in general, a good number of points will be required to estimate the value, because if we first approximate it by 1 point trapezoidal rule, the original function f of x will be replaced by phi. Obviously the result is different. If we increase it to 2-point formula, then first part the phi n will be this, and second part the phi n will be this. There will be again difference. As we go on increasing the number of points, the difference between f of x and the phi 1 of x would go on decreasing at each and every block. On the other hand, if we approximate the function by phi 2, then n is equal to 2 will give you the exact result, as this parabola, this section, as it is a parabola, already parabola, can be fitted by a single parabola, and n is equal to 2 gives you correct result. And for higher degree of polynomial, if we could replace the exact function under consideration by a suitable integrating polynomial, then convergent result is obtained with very few points. So this is a very important point, and that should be borne in mind while performing a program on integration, you may find that you are getting a convergent result with if you get a convergent result with very few number of points, then check the nature of the integrand and see whether it corroborates with your findings physically. If we say that the integrand is a complicated nonlinear function and you are getting a result which does not change appreciably by increasing n in trapezoidal rule, then there must be something wrong in the programming.